In the gradient descent algorithm, simply we will be using the derivative of the function as an information for us. Let's say we have design variables of x's. The vector is the capital X, and we will use the derivative information. But first of all, we will have actually a search algorithm to be able to change these x values by, so this initial, the new x values for k plus 1 is equivalent to current x values. K is the iteration number, kth iteration. It can start from 1, for instance. If this is 1, the left side is 2, plus an alpha, which is step size, and the search direction. And this is also for the kth iteration. So this is called search direction. This is step size. This is current point of the design variable. And this is new point. We will find the new point using the search direction, as you can see. And this search direction is important for us. And actually we use this gradient information or derivative information in here for S. And Sk, for instance, can be calculated as minus f prime x. F prime means the gradient, the derivative. And minus means it is going downward. So that's why it's called descent, gradient descent algorithm. If this is positive, then we can say it is gradient ascent algorithm. So for minimization, we usually use descent, gradient descent. For maximization, we use gradient ascent. And this is also shown as the gradient sign, fkx. K is the iteration number. This is called gradient or derivative. Derivative, or also it's called sensitivity. These are all called, sensitivity. These are all have the same meaning. So if we write this into here, then we will have xk plus 1 is equivalent to xk minus alpha, the step size. It can be constant or can be changing. In this class, we will assume that step size is constant at each iteration, and delta fkx. And when we write this, this becomes a gradient descent algorithm. So this is a useful, simple method, but there are some issues. Let's check them. It has slow convergence. When you get closer to the minimum, delta f, the gradient will get smaller. So it's not possible to catch minimum quickly. Also sensitive to the step size and initial point. So initial point here, this one, for example, initially we can try different values. It is sensitive to that. And also step size, this alpha is important to choose what the value might diverge if step size and initial point is not chosen correctly. So we have to be careful. Stopping criteria and optimality criteria should be chosen carefully. These are important as well. And there are some existence, uniqueness, convergence, and local optima problems. If we have derivative, and this is the simplest method with just one derivative information with constant step size, so the local optima can be a problem because it can stop at a local optima rather than going to the global one, because it assumes that the derivative will be 0 over there and it will stop there. The value will not change. So this is a problem. Divergence can happen, so convergence is a problem if we don't choose the correct initial point. We will solve an example about the gradient descent algorithm and unconstrained optimization. So we have this mathematical formulation with two design variables, and x1 and x2. We want to find the minimized point of this. And let's start with the solution as the so the initial point can be estimated a value, and also let's write solution first. And we know that our search algorithm will give us xk plus 1 is equivalent to xk minus the gradient descent, actually, fkx. So we need the derivative. That's why we can calculate the derivative of this first, f x1 x2. Basically, we will have the derivative based on x1 and also based on x2. That's why we will have maybe a vector. At the top, we will have derivative by x1, which becomes 1 minus x2. X2 is assumed constant, actually, and that's why it becomes 0. And that's why we have the third term. And from the third term, we will have plus 4x1. And 2x1, x2 becomes just 2x2 because x1 becomes 1 when we take the derivative, plus 2x2, and x2 square becomes 0 again because it's assumed constant, or there is no x1, so the x1 becomes 0, which makes x2 0. So this is the derivative based on x, and based on x2, we will have minus 1 for this. This becomes 0, and for this one we have again 0, and for the fourth one we will have 2x2, and for the last term we have 2x2. So these are the derivative information. Let's remove these. We will use the same derivative values, actually same derivative formulations at each iteration. So let's keep this in mind here. This can also be shown as the delta f divided by delta x1 and delta f divided by delta x2. Okay. Also, we will have an initial point. Let's say k equals 1. So let's write actual iteration k equals 1. Iteration k equals 1. Here we will have an initial point of x1 is equivalent to x1 and x2, 1, 1. So we will start with 0, 0. So you can change this, but I decided to start with this. And I want to use a step size of alpha equals 0.5. So here there is alpha, actually, which is 0.5. 0.5. Okay, let's use this. So what we need to calculate is this derivative for this initial point, so that we can use this formulation to find x's, because this xk, x1 is this now. We don't know this value. Let's find it. For this, so delta f1 is equivalent to, we will simply write down these into here and find the results. So from the first derivative we have 1 plus 4 times 0 plus 2 times 0. In the second one, minus 1 plus 2 times 0 plus 2 times 0, and this will be equivalent to plus 1 minus 1. This is the derivative. Let's write these all into this search direction algorithm. So x2 is equivalent to x1, which is 0, 0, minus alpha, it is 0.5 is set, and 1 minus 1. And from here, simply we will calculate the x2 as minus 0.5 and 0.5. Okay, now we will have the second iteration, but before that we need to check a convergence. Of course, we need to calculate the function value for these values as well. That's why let's calculate function value for minus point. Actually, we can calculate it with the 002. Let's do that first for initial value. So f00 is equivalent to 0 minus 0 plus 2 times 0 square plus 2 times 0 plus 0 square equals 0. And for minus 0.5 and 0.5, it's equivalent to, I will not write these again. Here simply just substitute minus 0.5 and 0.5 and you will get, actually let's write for the first one. For the other iterations I will not write that. So minus 0.5 minus positive x2 0.5 plus 2 times minus 0.5 square here, minus 2 times 0.5 times 0.5 plus 0.5 square. And from here the result is minus 0.75. Let's keep this in mind and let's check a convergence. For convergence, you can have different options. So I used here two options. One, I check the derivative. So for derivative, we will check the second iteration derivative. We will simply write here the minus 0.5 and 0.5. If you write them, the result is 1 plus 4 times minus 0.5 plus 2 times 0.5, and the second one minus 1 plus 2 times 0.5 plus 2 times 0.5. Actually, I think I wrote this wrong. This is 1. This is 1. That's why this value is minus 0.5. So it's 1 because here, here we are taking 2 times x1. x2 is becoming 1 and 2 times x1 remains. Okay, here also 0.5 we said, and if we calculate this, it's 0 minus 1. So this is not equivalent to 0, 0. If the derivative is 0, 0 for both, there is no moving direction. That means no derivative information is given. So this step will not go forward. So we have to stop there. Here, because it's 0 and minus 1, we can continue. The second option is the convergence of function values. So simply we will have an error check. F's actually. F2 minus F1 divided by F2, for instance. So this is F1, this is F2. If you write these down, minus 0.75 minus 0 divided by 0.75 minus, the result becomes 1. So this is greater than a certain threshold. We set usually like 0. Let's say a multiplication of 100 as well. So this will be like 100%. And this is greater than 0.1%, for instance. We set this as the threshold. This is greater than this. Then we continue until it becomes lower than this. Then continue. So you can check both of them or either of them. Actually, it's better to check this because the derivative may never be 0, but it can converge here, and we can stop at when this converges. Also, you can set a stopping criterion for the iteration number. For example, after 100 iterations, stop, no matter what the convergence is, to eliminate the computational cost. So this was the first iteration. Because we said we continue, we will continue on to this second iteration, and let's do that in the next slide. In iteration 2, k is 2. We actually calculated it, the derivative of 2 as 0 minus 1. Let's write it down here. If we have this, then our search algorithm will give us x3 is equivalent to x2. x2 was minus 0.5 and 0.5. In the previous slide we found it. This is x2 actually. And the step size 0.5 and the derivative information 0 minus 1. And from here x3 is minus 0.5 and 1. So let's calculate the function value from this. F minus 0.5, f3 actually. Oh, sorry, k is 2. But we are calculating f3, fk plus 1. Sorry about that. Let's write 3 because this is x3 that we found here. So minus 0.5 and 1. Calculated from the actual function result, it gives us minus 1. I didn't write the details. You can just check the function and plug this in and get the result. Let's check convergence now. Of course, we need to find the derivative 3 as well. And the derivative 3 is, if we write 0.5 and 1 to derivative functions, it becomes 1 and 0. I will not write the details. Check convergence. First, we will check derivative. This delta f3 actually the same. And because this is not equal to 0, then we can continue. Similarly, as a second condition, we will check the error. f3 minus f2 divided by f3 minus 1 plus 0.75 divided by minus 1. Actually, this is minus 75. That's why it becomes plus. So here 0.25 divided by 1, which gives us times 100 gives us 25%. And this is greater than the threshold of 0.1, for instance. Then we need to continue again. So let's go to the iteration 3, because we said continue here, we cannot stop. Let's go to iteration 3. I think we need to go to the next slide for it. In iteration 3, we have k equals 3, and we calculated delta f3 as 1 and 0. So let's keep this in mind. Let's check the search algorithm. x4 is equivalent to x3, which was minus 0.5 and 1. This is x3. And minus the step size is 0.5 again, constant for this question. And the derivative is 1, 0, as we wrote here to remember. And the result is minus 1 and 1. And for that, the f function, f4, for minus 1 and 1, is actually minus 1. And the derivative, the gradient f4, when we put these minus 1 and 1 to the gradient functions, it becomes minus 1 and 1. Minus 1, sorry. So let's check convergence. The first tool that we want to check was the gradient. Minus 1 and 1 actually. Minus 1. This is not equivalent to 0. Then that means we can continue according to this. For the second one, we have f4 minus f3 divided by f4, and these are minus 1 plus, actually not plus, again minus 1 divided by minus 1, and this is 0, and 0 means we have a smaller value than our threshold. Actually, even if we make 100%, it is 0%. So we found a value smaller than our threshold, which is 0.1%. Then we need to stop because it converged. Actually, we can see from the results that f3 was minus 1, f4 is also minus 1. So this is the minimum, it seems. It's stuck in here. So we cannot continue because it will give always the same result, minus 1. Then we will stop here. Converged. Then stop. So it doesn't mean, so it doesn't necessary to have this also equal this to stop. We can stop either of these satisfies. So this satisfied only, and we can stop. So then optimal. So the optimal point is x_opt is equivalent to minus 1 and 1, because for this we actually had the convergence. So we can stop here and we say that, okay, after third iteration we were able to find the result. And with this we finish this example by finding the optimum point, and the minimum is minus 1 for the function.